Welcome to this explainer. Today, we're driving into one of the absolute most mind-bending concepts in modern physics. We are talking about a literal bug in the mathematical code of our universe. A total glitch, where the very fabric of reality just breaks. Physicists call this glitch a singularity, and today we're going to see exactly how modern science is trying to kill infinity and patch this cosmic bug once and for all. Let's get into it.
So, what actually happens when the laws of physics break down? I mean, this is the exact question that keeps theoretical physicists up at night. Deep inside a black hole, or right at the very moment of the universe's birth, the classic rules of general relativity simply stop working. They literally throw an error code. But don't worry, because we're going to explore how science is rewriting that code.
Section 1. The Infinity Problem.
Okay, we really need to stop thinking of a singularity as a physical place and start treating it like what it really is, a mathematical glitch. You see, general relativity predicts these impossible infinities, points of absolute zero volume where gravity gets so intense it just destroys quantum information. But here's the catch. Quantum mechanics strictly forbids this. The quantum world dictates that information absolutely must be conserved, and it relies on this structured quantum foam at the smallest possible scales. So at the extreme edges of the cosmos, these two foundational systems completely clash.
Section 2. Fuzzballs and the Information Paradox. Now, what's really interesting here is how string theory offers a genuinely fascinating patch to this quantum glitch. It's called the fuzzball, and what it does is eliminate that impossible point of infinite density entirely. So instead of a zero-dimensional dot of infinite mass, the entire region inside the event horizon is an extended, sphere-like object made of vibrating strings. The event horizon isn't just an empty doorway to nowhere, it actually has a physical, fuzzy surface right at the boundary.
To really ground this super abstract theory, just think about this massive number. 4 times 10 to the 17th kilograms per cubic meter. That is the mean density of a typical stellar mass fuzzball. To put that into a relatable perspective, it's like taking the entirety of Mount Everest and squishing it down into a single sugar cube. It is an unimaginably extreme density, basically like a neutron star, but the absolutely vital takeaway here is that it is infinitely far from being infinite. The math actually works.
So why does this matter so much? Well, it essentially solves the notorious black hole information paradox. The universe doesn't just delete information. As matter and light fall onto one of these fuzzballs, their strings fuse and expand, becoming part of the fuzzball's quantum makeup. That data then safely tunnels up through the fuzzy surface and gets delicately encoded into outgoing Hawking radiation. The information is perfectly conserved, crisis averted.
Section 3. The holographic universe map.
All right. This quote from the ADS-CFT correspondence research is pretty dense, but let's break it down together. Imagine a 3D room filled with chaotic, heavy gravity. That's what we call the bulk. This mathematical duality essentially acts as a holographic dictionary. It projects all of that 3D gravitational chaos onto the flat 2D walls of the room, where gravity doesn't even exist. It's literally mapping extreme gravity into totally understandable quantum mechanics.
And I want to be clear, this mathematical duality isn't just some neat theoretical trick. It's an incredibly practical tool. Physicists are using it across modern physics right now. They're using it to understand the thermodynamics of black holes, to study strongly correlated electron systems, and even to test supergravity approximations. It proves, without a doubt, that quantum math can effectively describe heavy gravitational phenomena.
Section 4. The Cyclic Big Bounce.
Okay, so we've patched up black holes, but what about the ultimate singularity? I'm talking about the origin of the universe itself. It begs a really provocative question. What exactly lies on the other side? Because if the Big Bang wasn't a point of infinite density, then what in the world was it?
And this brilliantly illustrates the difference in thinking. The broken classical model basically crashes a pre-Big Bang phase into a catastrophic, completely disconnected singularity. But when you look at the ekpyrotic or bouncing cosmology model, it's a smooth, continuous curve. The universe transitions gracefully without the math ever breaking down.
So instead of starting from absolutely nothing, imagine a pre-existing contracting universe. This earlier phase goes through a very slow squeezing contraction, and rather than relying on rapid, chaotic inflation, this slow squeeze naturally irons out all the cosmic wrinkles, completely flattening and homogenizing the universe. Now, as the universe shrinks further and further down, it reaches an incredibly dense, compact state. In classical general relativity, this is exactly where that mathematical glitch tries to pop up. The universe is supposed to just collapse into an infinitely dense point and destroy everything. So, The crucial point here is the bounce. Right before infinite density is reached, extreme quantum forces kick in. Physicists call these non-perturbative effects. Basically, the underlying quantum fabric acts like a ridiculously powerful repulsive spring. The singularity is completely avoided and replaced by a quantum bounce.
This quantum bounce instantly flips the cosmic contraction into a phase of expansion. And the true beauty of this is that it maintains complete physical continuity. The universe's past isn't completely destroyed in some mathematical shredder. It flows smoothly right through the bounce and into our present phase of expansion.
And finally, a new classical space-time emerges. Because of that incredibly slow contraction phase we talked about earlier, the universe that bounces outward is highly organized, homogeneous, and isotropic. It actually solves all the exact same cosmological problems that the Big Bang plus inflation model tries to solve, but it does it through a drastically different, totally singularity-free mechanism. Section 5. Testing the quantum universe.
Of course, all this mind-bending theory is really only as good as our ability to actually test it. So scientists are turning to massive observatories like LIGO. When two black holes merge, they send crazy ripples through spacetime. If black holes are actually fuzzballs, researchers predict we'll see very specific markers in that data. We're talking about slower ring-down decay rates and structural echoes vibrating across spacetime. Finding those would basically prove that fuzzy surface exists.
Which brings us to the ultimate takeaway. Why should you care about all of this? Well, it matters because it strongly implies that singularities, those scary places where reality supposedly ends, are likely just illusions. The universe is a flawless, incredibly robust information system. It totally refuses to die in an infinity trap and instead uses quantum patches like vibrating strings and cosmic bounces to ensure information is preserved forever. So, I want to leave you with this final, mind-expanding thought. If the Big Bang wasn't actually a beginning, but simply a bounce from a previous cycle of contraction, how many times has our universe lived before? Thank you so much for joining me on this explainer. Keep questioning the cosmos.